It's my great pleasure to introduce, Noah, that's fantastic. Noah Fleming. Noah is a PhD student working with Tony Pitassi at the University of Toronto. And he works on proof complexity in general. And he's going to talk about proof complexity of practical integer programming. So without further ado, Noah, go ahead.
Yeah, thanks for the introduction, Vijay. So unfortunately, for those of you who have seen my fellows talk, this talk is going to be pretty similar to it. So I'm going to be talking about the proof complexity of practical integer programming. And this is based on very recent work with Goose and Pagliazzo, Pitassi, Robert, and Victorson. Okay, so the outline of my talk is as follows. So first, we're going to talk about using proof complexity for algorithm analysis. You're all probably familiar with this. Then I'll talk about the proof complexity of integer programming. And here I'll focus on cutting planes and branch and cut, and how branch and cut can be formalized using this stabbing planes proof system. And I'll try to motivate stabbing planes as like a query view of cutting planes. So like how DPLL is sort of a query version of tree-like resolution. And then to switch things up from my previous talk, I'll show you, hopefully if I have time, how to get short proofs of any unsatisfiable system of linear equations in cutting planes using this framework. All right, so algorithm analysis from proofs. So the general idea is if you have a class of algorithms, you can formalize it as a proof system. And this allows you to hide the practical details of the algorithm. And then lower bounds on the proofs in this proof system imply lower bounds on the runtime of that class of algorithms. So you've all seen this for CDCL, which can be formalized as resolution. One you might not be as familiar with is in integer programming. So you can formalize the Chvátal-Gomory cutting planes method as the cutting planes proof system. So we're going to be focusing more on integer programming. So what's integer programming? So here you're given a system of linear inequalities, and you're asked to find some integer solution to them. And because they're linear inequalities, we can view them as a polytope. And the problem becomes, given a polytope, find an integer point in it. So a classic way to solve this problem is these Chvátal-Gomory cutting planes. So to define that, I'll need the notion of a CG cut. So a half space, I'm going to say that a half space is valid for a polytope if every real solution in the polytope satisfies the half space. So here, this guy in yellow on the right is a valid half space. So given a valid half space with an integer where A is integer, but B can be any real number, a CG cut from this half space is obtained by like taking the ceiling of the right-hand side. So what does this do? Well, you can see it in the picture here. It shifts the valid half space inward. So it cuts out some of the non-integer points in the polytope, but it preserves all of the integer points. And this is just because A is integral. Okay. And this is, well, actually, I'll get to that in a minute. So Chvátal-Gomory cutting planes is just a method to heuristically add CG cuts to the polytope. And this is done until either an integer solution is found or the empty polytope is deduced. And if we deduce the empty polytope via these CG cuts, then this is a proof that there was no integer solution in the polytope, because all of these CG cuts just satisfy or preserve integer points. So Cook, Coulard, and Turan in the 80s observed this, and they formalized cutting planes as a proof system. So here, you're given a polytope that doesn't contain any integer solutions, and you're going to certify this fact. So a cutting planes proof of this fact, this is going to be a slightly different definition than what Paul gave, but it's equivalent. So a cutting planes proof of this fact is a sequence of polytopes, beginning with the initial one that you're given, and ending with the empty polytope, in such that each subsequent polytope is derived from a previous one by introducing a new CG cut. So here's a little example. So we start with P1, our initial polytope. Here's a valid half space. Here's the CG cut on it. You get P2, valid half space, CG cut, so on and so forth. P4, and then finally P5, the empty polytope. So this is a cutting planes proof of size 5. There's 5 polytopes in this sequence, and the proof size is just the number of polytopes in the sequence. This is polynomially equivalent to the number of bits you need to write down the proof. Yeah, and so in proof complexity, cutting planes is quite a powerful algebraic proof system, and it's very well studied. It has short proofs as the pigeonhole principle, and it can also simulate resolution. And in the 90s, exponential lower bounds were proved on it by Putlock. So in the right here, I have a little hierarchy of some popular proof systems. So the ones in green are those that we have super polynomial lower bounds on, and the ones in yellow, we don't yet. Okay,
quick question, Noah. Do you have a short description of the lower bound that Putlock proved? What is the class of formulas?
It's
that's okay.
These interpolant formulas. Basically, his method is it's this method of feasible interpolation that was introduced by Krychek. Right. You can turn cutting planes lower bounds into monotone real circuits, and they get lower bounds that way. So the formulas are somewhat, they're the clean coloring formulas. As Albert said. Okay, so cutting planes is very well studied in proof complexity, but it's not really used by itself in practical integer programming solving. So modern integer programming algorithms combine cutting planes with a branch and bound procedure into what's known as branch and cut. So again, branch and cut is going to solve the integer programming problem by doing the following 2 steps. So first, we branch, we break our polytope up into subpolytopes such that every integer solution is contained in one of these subpolytopes, P1 to Pk. So here's an example. Here's 2 half spaces, and there we've broken the polytope up into 2 polytopes. And in practice, this branching is either done in sort of a DPLL style, where we branch on the all the possible integer values to a variable, or we branch on like the Hamming weight of a subset of coordinates or something like that. But all the branching that's done in practice can be simulated by the following rule, where we pick an arbitrary half space and we branch on whether the half space is true or its integer negation is true. That is whether ax is greater than or equal to b, or ax is less than or equal to b minus 1. And then the second step is we cut. So we refine these polytopes that we got by additional cutting planes. And then, so here's a little example. There you go. And then we recurse on each of the polytopes that we got. Okay. And so in 2018, we introduced the stabbing planes proof system as a way to formalize practical branch and cut algorithms as a proof system. And you can kind of think about stabbing planes as an extension of DPLL to reason about linear inequalities. So I'll show you that in a minute. So to define stabbing planes, let's start with DPLL. So you all know this. I'll go through it really quick. So a DPLL refutation is just a decision tree refutation. So here's an unsatisfiable CNF formula. You pick a variable, you branch on whether it's true or false. Let's suppose that's false. Branch another variable. Let's suppose it's false again. And we violate a clause. So we're going to label that leaf with the violated clause. And you keep going, and eventually, you label every leaf with a violated clause. And this is a proof that the original CNF formula didn't have any integer solutions, or any solutions. Okay, so we're interested in the integer programming world. So we want to rephrase DPLL in this language. So first of all, here, I've just rewritten the previous CNF formula, this CNF formula, as an equivalent and equisatisfiable system of integer linear inequalities. Just using the standard transformation. Notice that on the right-hand side, we have a constraint for each variable saying that that variable falls between 0 and 1. And so DPLL in this world, oh yeah, first, so these are linear inequalities, so we can view this as a polytope, which is nice. So DPLL in this world corresponds to branching on whether, picking a variable and branching on whether that variable is less than or equal to 0 or greater than or equal to 1. And because we have these Boolean constraints saying that each variable is between 0 and 1, this is the same as just restricting to whether that variable is equal to 0 or equal to 1. And here in red, you can see the action that this query does on the polytope. So let's go down the left path where we've restricted to the left half space. So now we're just left with this single point here that's intersecting x1 is equal to 0. And we'll query again. We get the empty polytope. And we can repeat this process to derive the empty polytope at every leaf, right? And because each of these queries, branching on whether x1 is less than or equal to 0, greater than or equal to 1, observe that like any integer point satisfies one of these two. So because we've derived the empty polytope at each leaf, this is a refutation of the claim that the system of inequalities had an integer solution. All right, so stabbing planes, it's just the straightforward generalization of this to query integer linear inequalities. So rather than branching a single variable, now we pick an arbitrary integer linear inequality, and we branch on whether it's true, whether ax is greater or equal to b, or it's false, ax is less than or equal to b minus 1. And because a and b are integral, any integer solution is going to satisfy at least one of these two. Okay, so here's the action on the polytope. We introduce these two half spaces. We rule out the space in between them, the slab in between them, and we recurse on both sides. So let's go down the left path. Now we're at this polytope. Again, we query some half space, and we keep going until we derive the empty polytope. Now let's go back up and do the right side. So now we're at this polytope. We keep going. We derive the empty polytope at all the leaves. This is, again, a refutation of the claim that there was an integer point in this polytope. All right, so stabbing planes refutations are really simple. They're just decision tree refutations where you can query linear inequalities. And the size of the proof is just the number of queries in it. This was recently shown to be polynomially related to the bit complexity that's needed to write down the proof by deduction to y. All right. So I said that stabbing planes formalizes branch and cut. But if you remember, branch and cut also allowed for these cutting planes deductions. So we show that these cutting planes deductions are superfluous from the perspective of proof complexity because stabbing planes can just simulate cutting planes. And this is sort of surprising because stabbing planes is a tree-like proof system where you can't reuse things that you've derived, whereas cutting planes is DAG-like. You can reuse lines that you've derived. Okay, and in fact, we characterize cutting planes proofs as a subsystem of stabbing planes, which we call path-like stabbing planes. Okay, so a stabbing planes query, one of these branches that we saw, is path-like if one half of the query is the empty polytope. So this is not a path-like query because both sides are not empty, but this one is. The left side is empty, right? And yeah, so path-like stabbing planes is one where all the queries are path-like. We call it path-like because the proof looks like one long path. For every node, at least one of its children is the empty polytope. And yeah, so path-like stabbing planes is equal to cutting planes. To show this, we just want to show that every CG cut is a path-like query. So here's a CG cut. Ax is greater than b is the valid hyperplane, and then we have taking the ceiling of the right-hand side there. So now let's look at ax less than or equal to the ceiling of b minus 1. Clearly, this lies outside of the polytope. And so if you intersect it with the polytope, you get the empty polytope. And so the query AX is less than or equal to the ceiling of B minus 1, and AX greater or equal to the ceiling of B is a path-like query. And that shows that you can simulate cutting planes and stabbing planes. Okay, so yeah, so this raises a natural question. Can we separate the power of cutting planes from stabbing planes? Can we show that stabbing planes is significantly more powerful than cutting planes? So a natural candidate is the Seitan formulas. So these are the canonical system of mod 2 linear equations kind of studied in proof complexity. On one hand, we showed that stabbing planes has quasi-polynomial size proofs of the Seitan formulas. And on the other hand, it was long conjectured that these formulas require exponential complexity to refute in cutting planes. And this is pretty reasonable because Seitan is like the canonical hard example for many of the algebraic proof systems we study in proof complexity. So really surprisingly, last year, Deduce and Touari showed that there are actually quasi-polynomial sized cutting planes proofs of Seitan. And they did this by showing that you can translate the stabbing planes proof of Seitan into cutting planes. All right, so this raises a natural question. Can every stabbing planes proof be translated into cutting planes? So we give a partial answer to this. So we show that every stabbing planes star proof, so this is stabbing planes proof where the coefficients in the queries are quasi-polynomially bounded, so have magnitude at most n to the polylog n. So every stabbing plane star proof can be quasi-polynomially translated into a cutting planes proof. Okay, and we do this in 2 steps. So before I showed that cutting planes is equal to path-like stabbing planes, we actually show that it's equal to something that seems like it would be stronger than path-like stabbing planes, which we call face-like stabbing planes. So recall that path-like stabbing planes, you required that one side of the query was empty. In face-like stabbing planes, you weaken that. You require that one side of the query is a face of the polytope. So that is, let's suppose it's the AX equal to B minus 1 side. So, or AX less than or equal to B minus 1 side. So this is requiring that AX is equal to B minus 1, might not be empty, but AX strictly less than B minus 1 is empty. So on one half of the query, we restrict to a face of the polytope, and on the other half of the query, it's just arbitrary. Yeah. And so cutting planes is equal to this face-like stabbing planes. And then second, we show that any stabbing plane star proof can be turned into a face-like proof with at most a quasi-polynomial blow up in the size. And that completes the simulation. Okay, so this gives a nice corollary, which is that if we allow for a quasi-polynomial blow up, which might be a lot, we can kind of think of this stabbing plane star proof system as a query version of cutting planes, right? So just like how DPLL is the query version of tree-like resolution, you just branch out variables, stabbing plane star is kind of a query version of cutting planes where you branch on arbitrary integer linear inequalities. All right, and another corollary is that we get exponential lower bounds on the length of stabbing plane star proofs just by lifting the cutting plane's lower bounds to stabbing planes. And another corollary is that we get short refutations, quasi-polynomial size refutations of any unsatisfiable system of linear equations over a finite field in cutting planes. So yeah, so if I have time, I can show you guys this. Vijay, what do you think?
If it's
It'll
like
be
a minute
about
or
5
two.
minutes.
Oh no, maybe we'll take it offline. Is that okay?
Okay. Skip this. Okay, so I'll just end with some open problems. So on the right here, I have like the hierarchy of the proof systems that we've considered. So up at the very top, this RCP proof system is the DAG-like version of stabbing planes. It was introduced by Krychek. And this little red line here means that there's a quasi-polynomial simulation. So cutting planes can quasi-polynomially simulate stabbing plane star. Okay, so the first open question is whether we can reduce the quasi-polynomial in the simulation down to just polynomial. Another one is, can cutting planes quasi-polynomially simulate stabbing planes? Can we get rid of this assumption on the size of the coefficients? Also, so the translation of low coefficient stabbing planes, this stabbing plane star, into cutting planes naively causes a blow up in the size of the coefficients. So can we get rid of that blow up? Can we show that bounded coefficient cutting planes can simulate bounded coefficient stabbing planes? Then can either stabbing planes or cutting planes simulate the DAG-like version of stabbing planes, known as RCP? So cutting planes can't polynomially simulate it, but it's possible that it could quasi-polynomially simulate it. Another question is whether tree-like cutting planes can refute systems of linear equations. Can they refute like Cyton? Or are these formulas hard for tree-like cutting planes? And finally, can we build stabbing planes-based solvers? So stabbing planes gives a nice query-like model, just like DPLL, which, as everybody knows, is the backbone of modern solvers. So can we lift this intuition to stabbing planes? All right. Yeah, thanks.
Thank you, Noah, for a fantastic talk. Thank you. Questions, please.
I have a question.
Yeah, Moshe raised his hand. Yes, Moshe, go ahead, please.
So you talk about DPLL as kind of as a query language, but DPLL really usually will give it input formula have been reduced to 3CNF. So we have variable that really corresponds to not just to basic variable, but they correspond to clauses by themselves.
Mm-hmm.
That doesn't really this imply that DPLL is kind of almost closest to your stabbing calculus?
Sorry, I'm not sure I completely understand.
You take a general formula, and the way you reduce it to 3CNF, you create for every subformula.
Yeah, a new variable that encodes.
You add a new variable. Now, when you query that variable, you're really querying a subformula. And therefore, this seems to me to be actually quite closer to your stabbing calculus.
Yes, if you allow new variable introduction like this, it would seem to be kind of closer to like a resolution over clauses, which would be simulated at least by this. Yeah, it would be simulated by stabbing planes.
In fact, there used to be a big argument over the years between this kind of CNF solver and, so to speak, circuit solver. People said, no, we are losing the structure of the circuit. Let's solve directly on the initial circuit without doing the reduction to CNF. And that debate has died eventually. I think the reduction to CNF has won. And I think one reason it won, and I don't know if anybody studied it, is it has extra power because you branch on subformulas.
Yeah, that's true. It would seem to be significantly more powerful if you're allowed to branch on these subformulas.
Paul has a question. Paul, go ahead.
Oh, yeah.
Sure, it's actually, so it'd be, it's great talk. Can you just briefly sketch the ideas? I know you didn't have time to present them in full.
Yeah. So I can go back. So basically, the idea is it's similar to the Cyton upper bound if you know it. Basically, what you do is you're going to refute these systems of linear equations over a finite field in sort of a divide and conquer way. So you're going to start with an unsatisfiable system of linear equations. So I have one here on the left. This graph corresponds to each of the constraints. You get like a hyperedge, and you're just going to do a divide and conquer procedure. You're going to split it in half, and then you're going to recurse on the side. Well, you're going to split it in half. You're going to sum up that half of. You're going to sum up both of the constraints mod whatever finite field you're over. So I'll sum up the ones in the first half of the constraints mod the finite field. Oh, for some reason it stopped sharing. And this is going to give me a constraint. If I branch on.
Can you try sharing again?
Yeah, I am, but it's for some reason not letting me do it.
Okay, then I guess maybe if you're having trouble with that.
Yeah. It's a standard kind of divide and conquer algorithm. Basically, you divide your set of constraints into two halves. You sum them up, mod the finite field, sum up each half, mod the finite field, and then ask whether this sum, mod the finite field, is even, or I mean, in F2 it would be whether it's even or odd. Over a larger field, you'd ask what its modulus is, and then you'd recurse on the half that's unsatisfiable under this setting. And you can simulate this in stabbing planes by just branching on the value of this sum.
Okay, thank you.
I have a question, but Ian, can you start sharing your slides already?
Yep.
Yeah. Noah, I had a question regarding, recall that we had this discussion about interference-based proof systems. So you add a clause such that it doesn't preserve all solutions, but it preserves at least one.
Mm-hmm.
Sam Buss has studied those in the context of SAT. Similarly, in this context, it would be interesting when you add one of these GW cuts that you mentioned, or CG cuts, sorry. It would be interesting to see if you were to add cuts that preserve solutions, but not all solutions, preserve at least one solution, but not all solutions, and the corresponding proof systems that one could. You'll have to make an order to another solver that makes sure that the clause that you add or the CG cut that you add has the right properties. But in the meanwhile, I think Sam has another question. Sam, please go ahead and ask your question. Okay, so I'll read the question. Are there candidates for principles which are exponentially hard for SP?
Yeah, so the obvious ones, so all the lower bounds for cutting planes come from this interpolation result reducing to monotone circuit lower bounds. Because now we have this simulation of low weight stabbing planes by cutting planes, this shows that these lower bounds also hold for this low weight stabbing plane. So I think the natural candidate formulas for that should be hard for stabbing planes are just like anything you get via interpolation. So like clique co-clique or random CNF formulas or something like this. Yeah, that'd be my go-to.
Thank you, Noah. Thank you for a fantastic talk. Thank you very much.
Thanks.